Okay, let's talk about how to deal with these kinds of questions where not only are you calculating the amount of energy to change the temperature of a substance, but you're dealing with a situation, a scenario, where the substance is changing phases. Okay, so here's an example. Taking 50 grams of ice at negative 70 degrees and heating it to vapor at 300 degrees. Now, first of all, a quick definition of what I mean by going through a phase change. This is a useful thing to look at right here. This graph shows the phase changes that water goes through as it heats or cools. Now, this applies to all substances, but water is a particularly useful example, and it happens to be the example used in these calculation scenarios. Now, the thing is, in this previously mentioned scenario, you have ice, and it's asking how much energy to heat this ice that's at a really low temperature all the way up to vapor, aka steam, at a very high temperature. Well, the thing is, if you're talking about raising the temperature of something, as in raising the temperature of ice, or raising the temperature of water, liquid water, or raising the temperature of water vapor, you are talking about a scenario where you use Q equals mc delta T. For these changes in temperature, Q equals mc delta T. Delta T meaning change in temperature, delta meaning change. The temperature is changing, thus the equation works. But however, here, where ice is melting, or water is freezing, or here where water is condensing, or going from vapor to liquid, or when it is evaporating, vaporizing, going from liquid back into a vapor state, there is no temperature change. You can blast a block of ice with a blowtorch and it will stay at 0 degrees. You can leave a pot of boiling water on the stove, and as long as there's still water in there, it will stay at 100 degrees. It will not raise in temperature until all the water has boiled away. Likewise, this ice here, as it melts, will not rise above 0 degrees until all the ice has melted. Only when it is pure water will the temperature go up. So that means one type of calculation is necessary for when ice is melting or water is freezing. Or here another type when water is evaporating, or when water vapor is condensing, or when it's evaporating out back to vapor again. These phase changes have a different type of calculation than when you're heating or cooling a gas, a liquid, or a solid. So what that means is, if you want to find the energy to take some ice and heat it all the way to vapor, you have to find the energy to warm the ice up till the melting point, so that, because ice doesn't melt until it reaches its melting point. So that's one calculation. Another calculation for melting the ice, so now it's 2. And then another calculation for warming the water from 0 to 100, so now that's 3 calculations. And then once that water's at 100 degrees, a 4th calculation for vaporizing it, and then a 5th calculation for heating the vapor, aka steam, up to the desired temperature. Okay, so that means yes, potentially this could be a rather tedious calculation, but that doesn't mean it's difficult. So let's look at the process. And here are, again, these 5 questions we're going to look at. Another thing to consider as you look at these questions and how they relate to this, be aware that if you are heating it up, or otherwise adding energy, which is to say melting it, vaporizing it, or increasing the temperature, that's adding energy, you're going to calculate that the amount of energy required is a positive number if you are increasing its temperature, or if you are vaporizing it, if you are melting it. If, on the other hand, you are decreasing its temperature, you are removing energy from the system, which means you're going to calculate a negative energy number. That means if you are cooling it down, or condensing it from gas to a liquid, or freezing it from a liquid to a solid, all of those things involve removing energy from the system and will give you a negative value. Thus, looking at these questions, I can tell already, this one talks about adding energy because you're warming it up, and you're going to melt the ice, again adding energy, so this will be a positive number. This one involves releasing energy, So I can tell already this is going to be a negative answer, a negative number. This one, how much energy is required, that's going to be a positive number because it's going to be adding energy. This one's going to be adding energy. And this one, releasing energy, means that, okay, adding energy, positive number, adding energy, positive number, releasing energy, this will also have a negative answer. So, let's go through the process of how you solve these things and begin with the first one, that full process of going through the whole calculation from ice to vapor. Okay, so once again, let's look at this. This is saying you're starting with ice at negative 70 and you want to get to vapor all the way up here off the chart at 300 somewhere. That means you're going to have to warm the ice, melt the ice, warm the water, vaporize the water, and then warm the steam. Or should I say vapor? 5 calculations. Add them all together. That's how it's going to be. Here we go. So for warming the ice up to the melting point, okay, that's going to involve Q equals MC delta T. Q is the energy that I'm trying to find right here, and that energy is going to be in kilojoules. I need to pay attention to that for later. Mass is 50.0 grams. So I'll put that already, 50.0 grams times C. Well, what's C? Well, fortunately for you, the viewer, this will be given on the exam in a format similar to this. You need to use this, if you want to warm ice up, you need to know the specific heat of ice, which is 2.11 joules per gram degree Celsius. Joules per gram degree Celsius, so there it is. And then you multiply that by the change in temperature. Well, remember, ice melts at 0 and we're warming it up to its melting point. So since we're basically going from down here somewhere to here, it's going from negative 70 to 0, so that means the temperature is going up 70 degrees. Alright, now when you calculate that, you're going to get an answer in joules, because joules is in the units of specific heat. So it's about 7,385 joules. Oops. And then since it does ask for kilojoules, I'll convert this to kilojoules, which, okay, that's based on the idea that 1 kilojoule, kilo meaning 1,000, 1 kilojoule is equal to 1,000 joules. Just as a kilometer is equal to 1,000 meters, or a kilocalorie is equal to 1,000 calories. Or a kilogram is equal to 1,000 grams for that matter. Now, okay, that being done and said, let's see about what that comes out to. So actually, I'll guess I'll take sig figs into account. 3 sig figs, 3 sig figs. So that means 7.39 kilojoules to warm the ice. Okay, that's the first calculation. There's going to be 5 calculations plus adding them all together. It's going to make 6 steps. Okay, step 2, melt the ice. Now, warming the ice, you went from negative 70 degrees Celsius to 0 degrees Celsius. Melting the ice is no temperature change. Okay, so that means you are going to take the mass of the ice, 50.0 grams, and then convert to moles. So 1 mole of water is 18.02 grams. If you don't happen to know that off the top of your head, you can easily look it up on a periodic table. The mass of 1 oxygen plus 2 hydrogens. Anyway, okay, convert grams to moles, and then use this, which again is given on your exam. It'll look like this right here. Because you're melting ice, you use this number, the heat of fusion. 6.02 kilojoules per mole of ice. And by the way, I should also mention that so far all these numbers are positive because you're warming the ice, which means a positive delta T. And when you melt it, you're adding energy, which means a positive number of kilojoules, which means a positive answer so far. Okay, so this will give an answer in kilojoules as desired, and the answer comes out to 16.7 kilojoules. Alright, now that brings it to the next piece. Let's see, let's just... there we go, bring the computer back online. The next piece is, okay, now you have gone from ice to 0 degrees Celsius, from negative 70 to 0. You've now melted the ice. So looking at this, you've basically gone from here to here. Now I need to go from here to here. So what that means is now I need to warm that water from 0 degrees Celsius to 100. So warming the water. So since a temperature change is involved from 0 degrees Celsius to 100, that means you're going to have Q equals mc delta T again. And since you have Q equals mc delta T, we're going to say Q equals, which is to say the energy is equal to the mass, 50.0 grams, times the specific heat of water, okay, listed on your exam, 4.184 joules per gram degree Celsius, times, let's see, our delta T from 0 to 100, so that's times 100 degrees Celsius. That's the change in temperature. It went up by 100 degrees. And then you do that calculation, and what you wind up coming out with is, let's see, 20,920 joules. But again, since we're trying to get kilojoules for the final answer, I need to convert that. Where 1 kilojoule is 1,000 joules. And I just noticed, silly me, that I made a mistake up here on this one. 1 kilojoule is 1,000 joules. I pre-calculated this elsewhere, so this number is correct, but this divided by 1,000 will give this number right here. So, oops, that was a mistake. Mini brain part there. But anyway, continuing. Okay, this will give 20.9 kilojoules to warm the water up. Okay, after that, once you have warmed, at this point we have warmed the ice, melted the ice, warmed the water. Now to vaporize the water is the next step. So vaporize the water. Where you take the 50.0 grams and then convert to moles, where 1 mole is 18.02 grams. That's the molar mass of water. And then if you're going to vaporize the water, you got the 40.6 kilojoules per mole energy requirement. So grams cancel grams, moles cancel moles. Okay, and when you calculate that out, you're going to get about 113 kilojoules energy to evaporate that 50 grams of water. Okay, well, so far we have warmed the ice, melted the ice, warmed the water, vaporized the water. The question asks about warming the vapor up to 300 degrees Celsius, so that's the final step. Warm up the vapor. So, again, because that's from 100 degrees Celsius to 300 degrees Celsius, it means the temperature goes up by 200 degrees, and also that means we can use Q equals mc delta T because there is a delta T, unlike here with no temperature change. Alright, so warming up the vapor, that is 50.0 grams, so it's, well, I should say Q equals mc delta T. So mass is 50.0 grams, Q equals that times the specific heat of vapor, which is 2.00 joules per gram degree Celsius, times the delta T, it goes from 100 to 300, so that's an increase of 200 degrees Celsius. And when you do that calculation, it comes out to 20,000 joules, and then you convert that where 1,000 joules is equal to 1 kilojoule, and that gives you a 20.0 kilojoules. Alright, so 1, 2, 3, 4, 5 numbers. Well, total energy, add them all together. So 7.39 kilojoules to warm the ice, plus 16.7 kilojoules to melt the ice, plus 20.9 kilojoules to warm the water, plus 113 kilojoules to vaporize the water, plus 20.0 kilojoules to heat the vapor. And when you add all that together, it comes out to 178 kilojoules. Now I rounded it to 178 kilojoules because of significant figures, because of the fact that if you look here, that's 3 significant figures, and so we'll use 3 significant figures. And technically this also has 3 significant figures. This number we've been using, the 40.6 kilojoules per mole, or the 6.02, technically also has 3 significant figures, and 3 significant figures in the specific heats also. But at any rate, this demands this, 3 sig figs. Alright, so that's the first one. The second question, okay, question B, has to do with releasing energy. Now, fortunately, it's not quite so long and involved as the first one, because in the second one, what it's basically saying is that you are cooling it down. So first of all, you're going this way, but instead of all of it, it says you take 40 grams of water vapor at 100 degrees, so it's right here, and you cool it to water at 70, which means basically you just condense it and then cool it down to 70 degrees. So 1, 2 calculations, this is all we have to do, and then add them together. So here we go. Let's do 2 calculations and add them together for this part B, and pull that into view. There we go. Okay. Calculation number 1 will be condensing it from vapor back down to water. So there's no temperature change, so I'm going to take the 40.0 grams of water vapor, and let's see, condensing the vapor. I'll kind of label this first step here. There's the 40 grams, and then we convert that to moles, where 1 mole is 18.02 grams of water. And then the energy to condense it is negative 40.6 kilojoules per mole. Why negative? Because it's losing energy. When anything goes from a vapor to a liquid, it's condensing, and in order to do that, it has to lose energy. That's an exothermic process, which means a negative number for energy change. Negative, because it's exothermic. And then when you do this, you're going to get, a number in kilojoules, but here's the thing. The question's asking for joules. We've got to be careful about those units. So I'm going to add on one more step here, because grams cancels grams, moles cancels moles. I'm going to make sure that the final answer comes out in joules as requested by the question. So 1 kilojoule is 1,000 joules. That way kilojoules cancels kilojoules. And when you do this calculation, let's see, I guess we'll take into account the significant figures here. It comes out to about 90,122 joules. Sorry, negative 90,122 joules. Now, that's condensing the vapor. Now we got to cool it down from 100 degrees down to 70. So cooling the water. Cooling the liquid water from 100 degrees Celsius to 70 degrees Celsius. Alright, well, in order to do that, we're going to need, since we have a change in temperature, Q equals mc delta T, where Q is the energy and Q equals the mass of 50 grams, or 40 grams, 40.0, times the specific heat of water, for cooling water down. You look that up in your chart, it's 4.184 joules per gram degree Celsius. And then the delta T is from 100 down to 70, which means that it goes down 30 degrees. So delta T, it goes down, so that means 70 minus 100, because technically it's final temperature minus initial temperature. But either way, just subtract it out and make sure that if the temperature is going down, you get a negative number. Okay, as in the temperature is going down 30 degrees, so times negative 30 degrees Celsius temperature change. Now you do that, and it gives you an answer in joules that comes out to about 5,021 joules. About. Now, that being said, that's it. Okay, this joules right here is for this change, and this number of joules that here it is for this change, going down from 100 degree water to 70 degree water. So, oops, just noticed I forgot to put the negative sign there because it is a negative amount of joules. Now, here's what we do. We need to add these together for the total amount. Total, negative 90,122 joules plus a negative 5,021 joules is going to equal about negative 95,143 joules. Now, that's a really big number, and that's too big to write just like that, so we need to write this in scientific notation, and we need to round for significant figures anyway. So, I'm going to convert this to scientific notation with the correct significant figure. So don't not forget the negative sign. And I see 3 sig figs, so we're going to do, and since everything else doesn't have less than 3 significant figures, do 3 significant figures. 9.51. It's 1, 2, 3, 4. So times 10 to the 4th joules. So negative 9.51 times 10 to the 4th total energy change. That would be the answer. Okay, so when you do these, just pay attention to whether it's gaining or losing energy. That way you pay attention to whether it's positive or negative. And of course, pay attention. Do you have to do a calculation for just one segment of this, or 2, or 3, or all 5? Alright, now I'd like you, the viewer, to practice with some of these. Let's see. Let me pull up the original paper again. Here we go. Okay, here's what I'll do. I would like you to pause this and work on these last 3. I'll then put up the answers for each of those 3, and then maybe I'll just point out a couple key details about them. So pause it now and work on them. And having finished with them, here comes the answers to each of them. First, question C. Here's the fully worked out solution where it is in joules, and it was asking how much energy to take that ice at negative 20 and heat it to vapor at 200. So it wants to figure out how much energy to warm the ice, melt the ice, warm the water, vaporize the water, and then take it up to 200 degree vapor. So here's the calculation for energy to warm the ice, and then here's the energy to melt the ice, and then here's the energy to warm the water, liquid water. Here's the energy to vaporize that liquid water. Here's the energy to warm the vapor up from 100 to 200 degrees Celsius. So from 1 to 200, that's a 100 degree temperature increase. And When I add them all together, it comes out to that, with 3 significant figures for the because of some of the numbers used, especially this number right here has only 3 sig figs, and this number has only 3 sig figs. Thus, this number has 3 significant figures. So, next one, question D. Question D is asking about taking 50 grams of ice at negative 10 degrees Celsius and heating it to water at 0 degrees Celsius, which means warming the ice and then melting it. That's only 2 calculations right there. Just warm the ice and melt it. So, for part D, here is the answer. Let's see, I guess I'll just get this out of the way. Alright, there we go. So, this is the energy to warm the ice. This is the energy to melt the ice. Add them together, and you get this. Oops, I just realized 50.0. There we go, that part was missing. So 50 grams times specific heat times the temperature change from negative 10 to 0 is the energy to warm up the ice, and this is the energy to melt the ice. All right. So back to this question E. In question E, and I'll put this here to kind of aid with looking at what question E is asking about. Cooling 25 grams of water vapor from 100 down to 40 degrees Celsius to water at 400 degrees Celsius, at 40 degrees Celsius. So that means water vapor at 100 degrees is this right here. It's vapor, but it's at 100 degrees, which means you're condensing it, which means the opposite of vaporizing it, which means turning it into a liquid, and then cooling it from 100 down to 40 degrees Celsius. So that's 2 calculations you have to do, is condense it and then cool it down to 40. Well, first of all, joules released, that tells me this is going to be a negative number. So, let's look at what it came out as. Let's see, alright, just do this. Alright, condensing the water vapor. I use negative 40.6 because it's the opposite of vaporizing it. It's releasing energy, so it's negative. Converted to joules because it asks for joules. So that's the joules released when the water vapor condenses. And this is the number of joules released when you cool it down from 100 to 40. You subtract those two. That's a 60 degree temperature difference, which is why the delta T is negative 60, because it got 60 degrees colder. So you times all that out. You get this, you add these two together, and it comes out to that number, which we then convert to scientific notation, not forgetting the negative sign, and that's the total energy released, rounded to 3 sig figs, on account of the 3 sig figs here and 3 sig figs in various numbers that were used throughout the calculations. Alright, so there's a nice little overview. Happy studies.